See, in the last module, we had just started with time averaged of energy equations and introduced the concept of eddy momentum diffusivity and eddy thermal diffusivity. I will take a quick recap of what we had done in the last module. So, to the slides if we come, so this was the energy equation, general energy equation, where in which we neglected the pressure work, viscous dissipation, volumetric generation. Pressure work and viscous dissipation were neglected because the flow was incompressible, and volumetric generation we have neglected. So these were the terms which we had, we rearranged them, did the Reynolds averaging, we followed various steps, we just took the components, decomposed them into mean motion, fluctuating component, and wrote all those equations, time averaged those equations, and we got these terms. So when we time averaged, we ended up with this additional turbulent stresses. So if I write all of those equations, we got 5 equations and we got 17 unknowns, that is u bar, v bar, w bar, p bar, t bar, and these 12 unknowns. So this we termed as a closure problem. To make our life little easy, we took up boundary layer equations, that is considering turbulent flow near a wall parallel to a free stream, u infinity comma t infinity oriented in the positive x direction. So it's 3-dimensional, although it is 3-dimensional, we have neglected del by del z derivative of the time averaged quantities, and y momentum equation is neglected and z momentum equation does not exist, and the higher order terms are neglected, and we ended up with these 3 boundary layer equations. And we introduced here, we rearranged them, we rearranged these equations and wrote the eddy shear stress as minus rho u prime v prime bar as rho epsilon m del u bar by del y, as if it is like nu. Like we can write this as, for laminar flow we wrote this as rho nu del u bar by del y. So we have written epsilon m, but note that epsilon m is dependent on a fluid flow but not on fluid properties. So eddy heat flux was defined as minus rho Cp v prime t prime bar equal to rho Cp epsilon h del t bar by del y. So we rewrote this equation as u bar del u bar by del x plus v bar del u bar by del y equal to minus 1 by rho del p bar by del x plus del by del y of nu into nu plus epsilon m del u bar by del y, and energy equation as u bar del t bar by del x plus v bar del t bar by del y equal to del by del y of alpha epsilon h del t bar by del y. I just want to write this, remind you this thing by rewriting del apparent shear stress. I just want to write apparent shear stress, apparent shear stress. If you just see these equations, it's just the combination of both viscous and the turbulent shear stress, that is tau apparent is equal to mu del u bar by del y minus of rho u prime v prime bar, which is equal to rho nu plus epsilon m del u bar by del y. Similarly, apparent heat flux, is minus q apparent equal to k del t bar by del y minus of rho Cp v prime t prime bar equal to rho Cp alpha plus epsilon h del t bar by del y. M represents momentum, H represents heat flux. Okay, so that's how we have defined. So this is how we can visualize. So now if we get back to slides again, what are these slides saying? These are the 3 equations we have, as I said in the end in my last module. So you have 5 unknowns, that is u bar, v bar, p bar, t bar, epsilon m, epsilon h. These are 6 unknowns, but we have only 3 equations. So, how to close this with these 3 equations? How to find equations for epsilon m, epsilon h is called as turbulence modeling. So, that depends for each class of problem. Epsilon m and epsilon h will have different values depending on the class of the problem, that is whether it is internal or external or jet flows, it depends on that. So, now let us take up what, if you recollect, let me get back to slides. If you recollect, this was what I had projected. If you see this graph, u plus versus y plus I have plotted. I had given viscous sublayer, buffer layer and the turbulent layer. Now let us see, can we derive this? I am not going to derive 3 layer, I am going to derive 2 layer and then infer from that how 3 layer has originated. So let us get back to writing. So let us take up what is called as universal velocity distribution. Universal velocity distribution. So that is, if you take this was what I had written, tau apparent equal to rho nu epsilon m del u bar by del y. I am just writing now this, I am replacing this, I am just writing this implies tau wall by rho equal to nu plus epsilon m del u bar by del y, correct. So I am writing that here, tau wall by rho equal to nu plus epsilon m del u bar by del y. Now if you recollect, if you get back to slides, tau wall by rho, Pascal per kg per meter cube, Newton per meter squared upon kg per meter cube. Newton can be written as kg meter per second squared into 1 by meter squared kg per meter cube. It reduces to meter squared per second squared. That means tau wall by rho is recognized as frictional velocity. Yesterday we called this u tau equal to square root of tau wall by rho, and this we called it as frictional velocity. Now I will rearrange this equation in terms of u plus and y plus, that is the aim. So let us recollect, u plus was written as u by u tau and u tau equal to square root of tau wall by rho, and y plus equal to y u tau by nu. This is what we had written. So now left hand side of this equation becomes u tau squared, tau wall by rho you have, so u tau squared equal to nu plus epsilon m. For u bar, sorry, I have to write u plus is u bar by u tau, okay, I have just missed that bar. So u bar can be written as u plus into u tau, so del of u plus into u tau upon del of y can be written as y plus nu by u tau, so that is y plus nu by u tau. So but this u tau and nu are constant, I can pull them out. So nu plus epsilon m into u tau by nu by u tau into del u plus by del y plus, this is u tau square. So if I rewrite this, rearrange them, so you get u tau squared equal to nu plus epsilon m u tau squared by nu del u plus by del y plus. So we can say that this u tau squared gets cancelled out with u tau squared, and left hand side will be 1 equal to, and if I divide by nu, I get 1 plus epsilon m by nu whole bracket into del u plus by del y plus. Okay. So, this is my basic equation. Okay. So, let us take up this equation and consider, let us start with this equation and consider two-layer assumption. Let us consider two-layer assumption, that is two-layer assumption. Two-layer assumption. So, in the two-layer assumption we have laminar sublayer and second one is the turbulent boundary layer. I will not consider the buffer layer which I had, I will take only two layers, one is the laminar sublayer and the turbulent boundary layer. So, in the laminar sublayer, as you can recall, tau laminar exceeds the tau turbulent, and in turbulent boundary layer, tau turbulent exceeds the tau laminar, correct. So, in laminar sublayer, this equation, because 1 into del u by del plus, if you have to just say this is del u plus by del y plus epsilon m by nu del u plus by del y plus, this is what? This is tau laminar, and what is this? This is tau turbulent. So, in the viscous sublayer I can neglect this component. So, I have in the laminar sublayer or the viscous sublayer, in the laminar sublayer, tau laminar is greater than tau turbulent, which implies that 1 is equal to du plus by dy plus term. Okay. So, if I write this as du plus equal to dy plus, if I integrate this, u plus equal to y plus plus c, but we know that at y equal to 0, u equal to 0, which implies at y plus equal to 0, because y plus is nothing but y u tau by nu, u plus is nothing but u by u tau. When y is 0, y plus is 0, and when u is 0, u plus is 0. So, you get u plus is equal to 0. So, that this implies that c equal to 0. So, you get u plus equal to y plus, this is what we had written yesterday, u plus equal to y plus for laminar sublayer, correct. Now, let us take up, but this is u plus equal to y plus. Now, let us take up turbulent boundary layer. So, if I take up turbulent boundary layer, turbulent boundary layer. If I take up turbulent boundary layer, just you recall here, we had written this 1 plus epsilon m by nu du plus by dy plus. Now, this was the laminar shear stress and this is the turbulent shear stress. In the turbulent boundary layer, turbulent shear stress will be far highly exceeding compared to the laminar shear stress. So, I can neglect laminar shear stress and take only epsilon m by nu into du plus by dy plus. So, in the turbulent boundary layer, so I can write that as tau turbulent is greater than tau laminar, which implies that epsilon m by nu du plus by dy plus is equal to 1, is equal to 1. Now I need to invoke what is called Prandtl's mixing. I need to substitute relation for epsilon m. What I will do is, I will explain you Prandtl's mixing length little while from now. First, I will take up from Prandtl's mixing length the relation for epsilon m. From Prandtl's mixing length hypothesis or theory, epsilon m equal to kappa squared y squared du bar by dy mod. So, this is the relation which Prandtl has proposed for epsilon m. How, on what arguments this has come, I will explain a little later in this module only, but let us take this value. Now, before I substitute this here, I have to convert this epsilon m as, this is not y squared, this is, sorry, kappa squared y squared du bar by dy. I need to convert this y and u in terms of pluses before I substitute this in equation 1. Okay. So, I recall y plus equal to y u tau by nu and u plus equal to u bar by u tau. So, this implies that epsilon m equal to kappa squared, y squared can be written as y plus squared nu squared upon u tau squared, and du bar can be written as u tau du plus upon dy plus, y can be written as y plus nu upon u tau. This we have done earlier, so I have done little fast. So, epsilon m is equal to kappa squared, and here you see u tau squared gets cancelled out. So, nu squared by nu, you get nu, okay, into y plus squared into du plus by dy plus within the mod. Here I forgot to write the mod. Okay. So, this is the relation for epsilon m. Substituting this in 1, so what do I get? I get 1 equal to kappa squared nu y plus squared into du plus by dy plus mod upon nu into du plus by dy plus. So, as you can see, nu and nu get cancelled out. So, you get kappa squared y plus squared du plus by dy plus whole squared equal to 1. So, if I take square root of this, I am going to get kappa y plus du plus by dy plus is equal to 1. If I rearrange this, because I am looking for du plus equal to 1 upon kappa dy plus by y plus. Now, I can integrate this equation. Integrating this equation, I get u plus equal to 1 by kappa log of y plus b, and let me call this 1 by kappa as a. So, that is 1 by u plus equal to a log of y plus b. So, this is my equation which I have gotten, but who gives me a and b? A and b come from experiments. So, this is what is called as law of the wall. Law of the wall. Law of the wall, and if you compare with the experimental data, A equal to 2.5 and B equal to 5.5. So, this results, we started with 2 layers. So, what were those 2 layers? So, that is u plus equal to y plus for all y plus less than 11.6, that is between 0 to 11.6, and u plus equal to 2.5 log of y plus 5.5 for y plus greater than 11.6. This was proposed by, this two-layer structure was proposed by Prandtl and Taylor, and this is what is called two-layer model. Now the next three-layer model, this was refined by von Karman, and he gave three-layer model, which is what I taught you in the previous modules, that is u plus equal to y plus for y plus between 0 to 5 and u plus equal to 5 log y plus minus 3.05 for y plus between 5 to 30, which is buffer layer, and u plus equal to 2.5 log of y plus 5.5 for y plus greater than 30. This was given by von Karman, and this is three-layer model. So if I get back to my slides and compare these models with the experimental results, so this is, it shows that u plus y plus, you see the three-layer model, all these dots are experimental data. So you have three different lines. First line is viscous sublayer, the second one is the buffer layer, and the third one is the turbulent layer. Yes, so coefficients are slightly, there is a typo mistake here. So this is u plus equal to, in this graph, that's correct, this is 2.5 log of y plus 5.5. While I have copy pasted, I have made this mistake, please correct yourself. What I have written here is the correct one, or what I have shown, if I have to show you in the slides, what I am showing you in the slides here, this is the correct one. In the graph, there is a typographic mistake. So now the last one is the Prandtl's mixing length hypothesis. So which is what I had explained you, that is Prandtl's, let us take up Prandtl's mixing length hypothesis. So to the slides, you see I am just considering a shear flow, and you have the velocity profile here. You can have either v prime positive, that is a fluid particle moving from location y to upper location y, but it has moved by a distance of length L, or the fluid particle might have moved from top to bottom, which will induce v prime less than 0, then in that case u prime is greater than 0 and it has moved by a length L. So the order of magnitude of epsilon m can be discussed from the following scaling argument, which was proposed by Prandtl. In the boundary layer, imagine a ball of fluid that at some point in time is situated at a distance y, here in this case y, where the mean longitudinal velocity is, let's say, u bar y. Imagine next that this ball migrates towards the wall to a new location y minus L. So there it would be u bar y minus L, that is the mix. So what is L? L is the mixing length along which the ball of fluid maintains its identity. See, if you recall my video yesterday, and that is in the previous modules, I had told that the eddy size, you can think that L is kind of eddy, how long it is getting retained. So if you see that, because the velocity u prime, the order of u prime is velocity at y minus velocity y minus L, correct? So this is nothing but u of y minus of u of y minus L of del u bar by del y. This is just by Taylor's series expansion. I have neglected the higher order terms. So this and this gets cancelled out. So you get order of u prime as L del u bar by del y. Similarly, you can argue out that order of v prime is also of the same order. So L del u bar by del y. Okay. So minus u prime v prime bar will have the order of L squared del u bar by del y whole squared. Correct? So now if you recall epsilon m, what is epsilon m? Epsilon m minus rho u prime v prime bar is equal to epsilon m del u bar by del y. This is what we had taken. So this should be equal to L squared del u bar by del y whole squared. Correct? So you get the order of, that is the value of epsilon m is equal to L squared del u bar by del y. Okay, I have taken mod because negative signs and all are taken care. But now what should be the scale of the L? Scale of the L, if you take the pipe, it can be of the order of complete this y. Okay, but then L is of the order of y means L is equal to some constant into y, kappa. So this I write this as kappa squared y squared del u bar by del y. If you recall, 1 by kappa was my 1 by kappa squared was my value A. So kappa comes to approximately 0.4 or 0.41. So which says that kappa is of the order of actually 0 to 1. So kappa is of the value between 0 to 1 and the value of kappa is 0.41. So this is what is the Prandtl's mixing length hypothesis. If I come to the slide, so in the slide you can see that epsilon m equal to kappa squared y squared del u bar by del y. So this brings us the closure of turbulence averaging and the Reynolds shear stresses using Prandtl's mixing length theory. But next module we will see how using this universal velocity profile we can derive friction factor for smooth pipe and rough pipes. Thank you.